Welcome to the first video for the book, Electronics for Guitarists. I'm going to start out with a discussion on diodes and a little bit of semiconductor theory, but unlike most of the videos that will be coming up, this one is purely qualitative, no math whatsoever. So, with that in mind, let's get started. All right, in front of us, we see a collection of diodes and some specifications relating to them. Starting at the top, we have the schematic symbol for a diode. The left-hand side is the anode, the right-hand side is the cathode. And in a nutshell, the function of a diode is to allow current flow in one direction while blocking it in the other. On the left-hand side of this page, we have the 1N4148, which is a very common fast switching diode used in low power applications. It's got a breakdown voltage of 100 volts. That's what V sub BR means, reverse breakdown voltage. And it can carry a DC forward current of 300 milliamps. Now, forward current is current that flows through the diode in the direction that it normally would want to carry current. Okay, so using conventional current, that is current flowing from positive to negative, conventional current flows through a diode from left to right according to this symbol's orientation. We cannot force current flow back the other direction. That's called a reverse current, and it should be zero. Forward current for the 1N4148 should be limited to 300 milliamps. The next diode in the list is the 1N4004. This particular diode has a breakdown voltage of 400 volts, and it's designed to carry 1 amp of DC continuous current. There are a number of different diodes in the 1N4000 series. The 1N4004 happens to have a breakdown voltage of 400 volts, but there are other diodes. The 1N4001 has a breakdown of 50 volts. The 1N4007 has a breakdown voltage of 1,000 volts. But any diode in the 4000 series is designed to carry 1 amp. All right, the next diode over is the 1N5408. This has a breakdown voltage of 1,000 volts and is designed to carry 3 amps forward current. So it's basically just a higher current version of a 1N4007. And finally, on the right-hand side, we have a 1N34A. Now this is a germanium point contact diode. In contrast to all the 3 diodes on the left, these are silicon PN junction diodes. That's what you're going to find in almost every application today. Very few germanium diodes or point contact diodes. But I included it here because it's an interesting device and they're still used out there in some applications. This particular diode has a breakdown voltage of 20 volts and can carry a forward current of about 50 milliamps. All right, now, before I go on, I'm going to talk a little bit about silicon, and let me show you a silicon wafer. All right, this particular wafer is one that I did some processing on at Penn State University a few years ago. And I don't know if you can see it, but there is a Penn State Nittany Lion on here and a few test squares, but they're very difficult to see because I didn't take it through the entire fabrication process. Just a little bit of vacuum deposition of titanium and some masking and so on. But anyway, this is a wafer that I processed a bit. Let me show you another one. here is a silicon wafer that, this was fabricated back in the 70s. This would be for a static RAM chip that is a memory device compatible with TTL logic. And this is a 4-inch wafer. Here's a broken wafer. Silicon is very brittle, and if you drop it, it'll shatter just like glass. And that's what happened to this one. This was, I believe, some TTL devices, maybe some NAND gates or quad NOR gates or something like that. Maybe even JK flip-flops. I can't remember. But this is what happens if you drop a silicon wafer. It shatters. Now, here's a little bigger wafer, a little more current. This is, I believe it was a modem chip. I'm not certain, but you can see it's a much bigger wafer. This is a 5-inch wafer. And it's got a much, much higher fabrication density than the other two, but it's an example of a larger wafer. And finally, I have an example of a really big wafer. This is a 7.5-inch wafer that I believe was some sort of modem or maybe even a microprocessor. I'm not certain, but this is a pretty big wafer, and it's very fragile. But this is to give you an idea of what silicon looks like. And you can hear it's kind of like a cross between a metallic and a glass sort of sound. But in any case, I thought you might like to see these. All right, now, all this talk about silicon, what are we looking at? Well, let's start with this representation. Okay, what I've got here are simplified cartoon versions of silicon, arsenic, and boron. All right, starting with silicon. This is the main semiconductor material used today, and it's, as you can see, atomic number 14. That means it has 14 protons in the nucleus. And it's also going to have 14 electrons orbiting around it. Now, in this view, I'm condensing all of the inner electrons and the nucleus into this center circle marked Si for silicon. All we see orbiting around it are the valence electrons. Silicon has 4 valence electrons. Those are the electrons in the outermost shell. All right, these are the electrons that determine the electrical characteristics and the chemical properties of silicon or any other atom. All of the chemical and electrical properties of an atom are essentially determined by its valence electrons, the outermost electrons associated with that atom. Okay, so now remember, there are a total of 14 electrons, but I'm only showing the outer 4 in the valence band. All right, so it's a group 4 element because it has 4 valence electrons. Now, a couple of other atoms or elements that we're going to be dealing with are arsenic, which is atomic number 33. And again, all of its inner shells and nucleus are condensed into that center AS circle. And it's got 5 valence electrons. So this is called a pentavalent atom. All right, it's group 5, has 5 electrons in its valence shell, and it's typically used as an N-type dopant with silicon to form semiconductors like diodes and transistors. This is also known as a donor-type dopant. When we add a different material to silicon to change its electrical characteristics, those additives are called dopants. And finally, on the right, we have boron, which is a group 3 element. So it only has 3 valence electrons. And I'm showing this 4th position empty because it would like to have an electron there. Actually, all of these atoms would like to have 8 electrons in their valence bands, but in order to maintain electrical neutrality, silicon has 4, arsenic has 5, boron has 3. All right, let's move on and talk about pure silicon for a minute. All right, if we melt silicon and let it solidify, it forms a regular crystalline structure, and in this case it's just a one-dimensional cross section. Again, this is really a cartoon view of it, but notice that any particular silicon atom in this lattice lines up with its neighbors such that it almost is like it has 8 valence electrons. Silicon would like 8 electrons in its valence band. It can't do that on its own because that makes it electrically charged, makes it an ion, but when it forms a crystal, it can align with its neighbors such that it acts like it has 8 electrons in its outer valence shell, which is what it would like to have. So it forms this regular crystalline structure, and this is called covalent bonding, okay? The neighboring atoms are sharing valence electrons, so it's covalent bonding. All right, now, one of the interesting things about pure silicon, we know it's called a semiconductor, but if I were to apply a potential difference across this crystal, I'd get almost no current flow through this thing. Current flow would be the movement of electrons from atom to atom crossing out and getting filled in by the battery or whatever on the other side. All of these electrons inside here are taking part in the covalent bond, so they are not available to act as charge carriers through this crystal. It takes a lot of energy to remove an electron from this structure and get it to flow through the crystal. Now, that means that pure silicon is really a terrible conductor. It's almost, a pure insulator. Now, occasionally what happens is that since it's not at absolute zero, there's going to be some thermal agitation, and once in a while an electron will get knocked out of the valence band, and that will be available as a charge carrier through the crystal. Okay, that thermally generated charge carrier constitutes a leakage current through the crystal, and we just call that leakage current. Now, if you look at this diagram also, at the edge of the crystal where it no longer has any silicon atoms to bond with, we also have some electrons that are available to move and act as charge carriers on the surface of the crystal. Remember, this is just a slice, a two-dimensional cross-section. But all of these atoms on the edge of the crystal have electrons that are not taking place in the covalent bonding process. So these electrons on the edge can also flow. That's called surface leakage. All right, so there we go. Let's move on. If we add a little bit of arsenic when we melt this silicon and then let it solidify, the arsenic will fit right into the crystalline structure with very little trouble. Now, when we're doping silicon with arsenic, we add very, very little arsenic, typically on the order of 1 part per million. So something like for every million silicon atoms, we'll have 1 arsenic atom. Those are pretty, common doping levels. Now, I've exaggerated it here, and I've thrown a few random arsenic atoms in there at much higher concentration that you would find in a real semiconductor, but It's just to prove, illustrate what's going on here. All right, so everywhere that an arsenic atom has taken the place of a silicon atom in the crystal lattice, we have an extra electron, and I've marked them with blue. And these electrons are very weakly held in the crystal structure and can act as charge carriers and move through the crystal with very little potential difference across the device. All right, now, since we have a relative abundance of these extra electrons donated by the arsenic atoms, they are called majority carriers. Most of the current flow through an N-type silicon crystal will be due to the movement of these extra electrons donated by arsenic. They are the majority charge carriers in that crystal. Now, again, thermal carriers will be generated too, but not nearly as many as there are these donated electrons. So the thermally generated carriers are called minority carriers. Okay, and they will consist of holes that are formed whenever an electron jumps out of the valence band, and they can propagate through the crystal as charge carriers as well. Now, P-type silicon is formed by adding a trivalent or group 3 dopant, such as boron, to silicon and allowing it to solidify and form the crystalline structure that it forms. Now here I have some random boron atoms placed in the crystal lattice, and notice that the boron has a missing electron, and these are called holes. These holes are free to move through the crystal just like electrons can move through the N-type crystal. Holes act like positive charge carriers, and they move the opposite direction of electrons. So if electrons moved this direction, holes would move this direction. All right, now, when we form a single crystal of silicon with N-type dopants on the right side, P-type dopants on the left side, we form a PN junction device, which is a diode. Now, what's going to happen here is that we've got all these excess electrons on the N-type side, and we've got an excess of holes on the P-type side. And what's going to happen is that electrons will diffuse to the left, holes will tend to diffuse to the right, and they will recombine. All right, so we get a diffusion current as soon as we form this PN junction. This forms something called a depletion region. All right, now what is a depletion region? Well, it's an area right around the junction between the P and N sides of the crystal, where electrons have diffused across and fallen into holes with the boron atoms, and likewise holes have diffused across and recombined with electrons in the N-type region. This is called a depletion region because everywhere that an electron has recombined with a hole, there are no longer any free charge carriers available. So, while the intrinsic silicon is a terrible conductor, but P-type silicon and N-type silicon are good conductors, the depletion region has no charge carriers, so it acts as an insulator between the P and N regions of the device. Here's another look at it. What we've got is some arsenic atoms around the junction and some boron atoms on the other side of the junction. These ones have recombined holes and electrons, and as that occurs, an electric field builds up around the depletion region that opposes any further diffusion. So diffusion stops a small distance away from the p-n junction. It forms an electric field that's called the barrier potential. For silicon devices, the barrier potential is about 0.7 volts. If we happen to use germanium instead of silicon, the barrier potential would be about 0.3 volts. All right, so there's a little bit about semiconductor theory with no math. All right, here's a diode in a circuit. All right, I'm ending with this just to show a little bit of the notation that I'm going to be using and some of the symbology. But on the left, we've got a battery that's connected to a resistor and a diode. All right, the battery has a voltage associated with it that I'm going to call V in. Now, I like to use voltage sensing arrows associated with my voltage names. If the arrowhead is pointing to the positive terminal of a battery, then V in is a positive value. If the arrowhead was pointing to the negative side, V in would be a negative value. I like to indicate currents with an arrowhead inside the wire, and they point generally in the direction of conventional current flow. So we're assuming that current flows out the positive terminal of the battery, through the resistor and the diode, back to the negative terminal. So we have a closed circuit. Current flow through this circuit is going to cause a voltage drop across the resistor with this polarity. If I put a voltage sensing arrow here, which is just like a voltmeter, the arrow's pointing to the positive end, so V sub R1, the voltage drop across R1, is a positive value. Likewise, the current flows down through the diode, I'm assuming at this point, which would cause the diode to have a drop where its anode is positive with respect to its cathode. So voltage from anode to cathode is a positive voltage as well. V sub AK means the voltage at the anode with respect to the cathode. Or you could think of it as V sub A, the anode voltage, minus the cathode voltage. All right, we'll see this more and more in future videos, and it'll all make more sense to you. But for right now, that's a quick run through of some diode theory, a little bit of semiconductor theory, and it's not the most exciting topic, I admit that. I've probably given introductory lectures on diodes and p-n junctions 100 times, and I'm never really excited about it, and it's just, it's just something that I wanted to get out of the way so we can move on to more interesting things. And there you go for this video. I may change the format somewhat in the future, hopefully, use more computer animation and, a little bit more interesting video effects and so on. But for right now, let's see how this goes. And if you hate this video, let me know. If you thought it was okay, at least don't say you hated it unless you did. Thanks, and we'll see you for the next one.